G'day everyone. In November 2018, the Queensland branch of the AEVA held the EV Expo at the Brisbane Convention Centre. This displayed a wide range of electric vehicles and had a bunch of presentations from experts in the industry. And this video is just a couple of those experts and what they had to say. If you're interested in coming to the Queensland branch monthly meeting, it's on the third Wednesday of each month at 7:30 at the Albion Peace Centre. I hope you enjoy the video and I'll see you on the next one.
So without further ado, I'm going to introduce my first speaker. Chris Jones is a very interesting character. Started off as a chemist and ended up as a battery engineer. Is that correct? So just a round of applause just for that alone.
Okay, so thanks everyone, and thanks for coming along. What an awesome turnout. Brisbane guys have just done an amazing job, and I think, we'll go away from this going, that was totally worth it. My doctorate was actually in plant biochemistry and genetics. So my Bachelor of Science was in chemistry, moved into plant science when I moved to Perth, and I'm now working, my job title is battery engineer, but I should point out I'm not an engineer. That's just the job title. But I work for a company that's developing a new battery technology, and it's quite interesting. But a lot of what I do in my job is scan the literature on battery technology, what's going on in the peer-reviewed scientific world, and then trying to sort of distill that into how we can apply that to battery technology in the future. So this presentation is kind of like a bit of a distillation of all of that information I've been gleaning, and if I can share it with a wider community, then so the better. So yes, the chemistry and physics of lithium-ion rechargeable batteries. So I'm going to talk science here. So it contains chemistry, maths, physics, engineering, materials science. Certain MPs and senators don't like that kind of stuff, with the exception of Tim, obviously. But this stuff's real. And nomenclature, I'm talking about the cell. So the cell is the fundamental unit of a battery. It is the single 3.7 or 3.2 volt unit that stores energy. As soon as you put more than one of these in series or in parallel, you've now got a battery. And so I've kind of put some pictures up there of examples of what I mean by a cell, what I mean by a battery or a module, and then the pack. And the pack refers to the entire enclosure and all of the safety equipment contained therein. So you'll often hear people talking about energy density. You also need to remember, are they talking about it at the cell level or are they talking about it at the pack level? Because obviously at the pack level the energy density will decrease. So that's just some examples of prismatic cells over there on the left, pouch cells in the middle, and cylindrical cells on the right. All chemical reactions involve the transfer of electrons. If electrons aren't moving, there's no chemistry happening. So the basic principle of an electrochemical cell is harnessing the movement of those electrons as the chemical reaction happens. Now you could put all of those ingredients in the one flask and shake it up, and the same chemistry is still going to happen. You just won't be able to harness the electrons. But if you separate them, as they have in this case of the zinc copper cell, you can then make use of that electric potential and drive things. And in the case of a primary cell, which is what this is, the reactions are not reversible. So certain reactions are, and lithium-ion is one of them. So yes, we put this electron transfer to work. That's how they work. And lithium-ion cells are no different, except in the case of a lithium-ion cell, it's reversible. We can apply an electric potential and we can push the lithium ions one way or the other. When we charge a lithium ion cell, we're pushing lithium ions into the anode, where the ions are intercalated by, in this case, the graphite structure. And they stay there, thanks to the separator and the electrolyte we've got in there. And they won't move until you complete the circuit at the top, and they'll head back the other way. Right. So the example that's given there is the lithium cobalt oxide cell. This is the original lithium-ion cell. The laboratory of John Goodenough published this work in 1981. So that's how long the lithium-ion cell has been around for, and it's probably been in production since about the late 1980s. He also did some work in 1997 on olivines, which is lithium iron phosphate as we now know it. So yeah, the chemistry's been around for a while, and we've known about what it was capable of for quite some time. And most of the gains that we've had in lithium-ion chemistry have actually been in the cost-effective manufacture and reliable manufacture of the cells. The cathode is the single most expensive part of a lithium-ion cell. It contains all of the expensive bits. So cobalt is a very expensive metal, but it makes for some really good batteries. Manganese, it's certainly cheaper. It's got its bonuses and pluses and minuses. But ultimately what we're talking about is a crystalline structure which can intercalate lithium ions. When we discharge a cell and we charge the cell, they move into that crystal lattice. And certain metal oxide crystals make room for lithium ions better than others. So lithium cobalt oxide is commonly known as LiPo to those of us in the know. Or lithium polymer. It's basically still using a lithium cobalt oxide anode. In the case of iron phosphate, it's a slightly different crystal structure, and the lithium ions intercalate in a slightly different way, and you can't fit quite as many of them. And then there's other combinations, NCM and nickel manganese. An awful lot of carbon black goes into it. So when you look at the surface of an anode, it's just black stuff painted on a piece of aluminium. PVDF, polyvinyl difluoride binder, is what holds it all together so that it doesn't all sort of wash off as soon as you assemble the battery. They're typically coated onto an aluminium current collector, and that becomes the positive terminal of the cell. The electrolyte, which is the liquid that joins the anode and the cathode, that's what dissolves the lithium ions. Typically, the lithium ion source is lithium phosphohexafluoride. It's chosen because it dissolves in this unique ethylene carbonate-based solvent that is the electrolyte. This molecule here, it's quite volatile, but amazingly it dissolves some pretty high concentrations of this particular lithium salt. And so that's what basically forms the ion transfer between the two plates of the cell. Now, some work by Jeff Dunn over at the University of Dalhousie in Canada found that if you put fluorinated versions of this solvent in the mix, it's got far better heat tolerance, and you won't get decomposition of the electrolyte. What is interesting is that when the electrolyte decomposes, it forms carbon dioxide gas and it builds up pressure. And if you've got radio-controlled cars and you've got your pouch cells, they might swell up and puff. That's largely carbon dioxide being caused by the decomposition of the electrolyte. It's highly flammable, and usually when there's a lithium-ion battery fire, it's the electrolyte that's burning in a hurry. The other slightly concerning thing about lithium phosphohexafluoride is that when it reacts with water and heat, it generates hydrofluoric acid, which is not good for you, and likewise lithium hydroxide, it's lye, so it could dissolve your skin as you expose yourself to it. The anode, that's the negative end. It's typically made of copper, copper being a good conductor, but also rather heavy. Graphite is typically coated on with PVDF as a binder, and that serves as the intercalation matrix for the lithium ions during charge. What's interesting is that as soon as the lithium ions are pushed into the the anode of the cell, they form this, what's called the solid electrolyte interface, the SEI. And it's a whole bunch of crud, basically. These crystalline versions of lithium carbonate, lithium fluoride, all these lithium salts form a mud that kind of coats the surface of the anode. But it's kind of a blessing in disguise because that actually protects that structure from collapsing, so it's able to maintain its integrity for longer. So although it does slow down the passage of ions, it actually retains them better. Really interesting thing about the anode is that the greatest gains we'll ever get in energy density will come from improvements at the anode. So things like lithium sulfur, lithium metal, using direct lithium metal as the anode has the highest energy density. You can store the most charge on that plate. The downside, of course, being a whole bunch of other side reactions that complicate the matter and basically result in a short-lived battery. But researchers are working on it. So the power or range, you can't have both. So lithium-ion cells, we've more or less hit a practical limit of about 265 watt-hours per kilogram. There are some that are a bit better, but it's a trade-off between discharge capability and energy density. And you'll see I've plotted on the graph there a variety of different commercially available cells. Specific energy up here in watt-hours per kilogram. So this is, if you want to drive a really long way, you want cells that are out here. But, you know, the trade-off is that you end up with very low power. They can't discharge very well without generating a lot of heat. At the other end of the spectrum, these are lithium cobalt cells. They can put out 30C or 30 times their capacity in amps. But the specific energy is not that flash. So the sort of bleeding edge of energy density and power is here. But I should point out this is more of a curve. If you filled it in with more data points, it would form kind of an asymptote. So yeah, watt-hours per litre is a different measure. It can be quite similar to the watt-hours per kilogram values, but generally cylindrical cells have far better volumetric energy density than prismatic or pouch cells. And that comes from the fact that they are wound up and stuck inside a can, and they're constrained. So that means that there's very little change in volume over the life of the cell as it's charged and discharged. Whereas a pouch cell or a prismatic cell has far more room to expand, and its energy density effectively decreases. But yeah, this is an interesting chart, and it's basically the challenge for battery engineers is to come up with a number that's out here somewhere. And by comparison, obviously, lead acid and nickel metal hydride batteries are way down here. So, what defines the energy density of a cell is pretty much the thickness of the aluminium and the copper. So, the aluminium and the copper are the current collectors. They move the electrons through the load circuit and back to the other side. The thicker they are, the more current they can handle and the more power they can deliver. But the thicker they are, the less room you've got for active material to store those lithium ions. So this chart basically plots that a cell's power is going to be kind of inversely related to the thickness of the layers that you've got of the active material. And there's similar plots there for energy density on a per gram basis as well. So this was a really nice paper that kind of summarised that. So it just comes down to how you pack it out. How do you improve the conductivity of a battery cell which has lots of active material in it? You can use things like graphene or a very conductive carbon-based anode, or as we move towards lithium metal anodes. So the other rule that applies is Ohm's law. That V equals IR, the current and the resistance determine the voltage. And the internal resistance of a cell is ultimately why it gets hot as it discharges. And the more energy dense cells have much higher internal resistances, and as a result, they generate more heat when you ask more current of them. So it's a parabolic relationship. If you discharge one of these cells at 3 amps, it generates, almost a watt of heat. But if you only double the current, you will quadruple the amount of heat being generated in the cell. So, yeah, internal resistance is basically the enemy, but if you want energy density, you have to accept some reasonably high level of internal resistance. And the internal resistance of a cell changes depending on where it's being discharged. At a fully charged cell will have a higher internal resistance than one that's sitting in a mid state of charge. And then, of course, that internal resistance increases again as the ions start to feel their way back over to the cathode. Unfortunately, that didn't carry through, but basically, Arrhenius's law says that the chemistry of any chemistry will happen faster with higher temperatures. Basically, an increase in temperature of 10 degrees Celsius is enough to double the reaction rate. Now that works as well for good chemistry as well as degrading chemistry. So if you park your car fully charged in a hot sunny day, you're going to increase the rate of degrading reactions in the battery, and they won't last as long. So, and that kind of ties into what I mentioned in the previous slide about Ohm's law. If you've got really high energy density cells, they're going to generate a lot of heat under fairly ordinary use. So you need some kind of a thermal management system so that they don't get too hot and have a short life. And Jeff Dahn has done some fantastic presentations on this. You look up a YouTube video called "Why Do Lithium-Ion Cells Die?" And set aside a good hour to watch it. It's a really informative discussion. So, thermal management, this is a bit more physics. Basically, the area of the thing that you're passing heat through is going to be critical. The thickness of the thing that you're passing the heat through, and of course the K in that equation there is the thermal conductivity of material. So by way of comparison, copper has a thermal conductivity of about 300 watts per metre Kelvin, aluminium 200 watts per metre Kelvin, plastic about 0.2, 0.4. A really, really thermally conductive epoxy will be about 1. So the reason why I mention plastics is because they don't conduct electricity, which is a good thing. If you're going to be trying to hold a cooling plate up against a cell, you don't want it to be conductive because it will potentially short the cell. So Tesla battery packs have very good thermal management systems, but they still have this rubbery kind of stuff between the cooling channel and the cells that is electrically insulating but moderately thermally conductive. And it's never as good as we'd like it to be, but them's the laws of physics. So, as I said, the key to battery longevity is going to be maintaining it in that really sweet sort of 20 to 25 degree spot. If they're too cold, the chemistry is sluggish because the internal resistance increases. If it's too hot, you risk putting the cell into a thermal runaway and you've got a big fire on your hands. So, looking to the future, it looks like silicon and lithium metal anodes are going to be the next genuine step in energy density. I should point out, energy density hasn't really changed a great deal in recent times. Batteries haven't necessarily gotten cheaper, but they've certainly gotten better. So, you can get more watt hours per kilogram or per litre for your battery for about the same money as you would have spent last time. They have gotten cheaper to manufacture, and they've certainly gotten cheaper for the likes of General Motors and for Tesla, but they're not getting cheaper for us. But they're getting better. There are some novel cooling strategies out there, including immersion of battery packs in dielectric fluids like Novec and other fluorinated compounds. They don't react with anything else, but they're also pretty ordinary at absorbing heat, so swings and roundabouts. The other advances, of course, have been being able to manufacture cells cheaply and more reliably. That's been a big driver of the cost reductions. And we're also looking at cheaper and more abundant feedstocks, so limiting the amount of cobalt that goes into the metal oxide layers of the cathode, for example. So I thought I'd just leave this slide here. Eric sent it through the other day. That cell on the right is the old Thundersky cell. It had an energy density of about 100 watt hours per kilogram. I think that particular one was probably around about 90. The ones on the other side are around about 200 watt hours per kilogram. So yeah, we've literally doubled energy density in the 10 or so years that we've been working with lithium batteries. So thank you.
G'day everyone. Let me just play with the IT here for a moment. Okay. Can everyone hear me? Yes? Good. All right. Thank you to the AEVA for the opportunity to speak today. I've had a long-standing association with the association, but today I'm here wearing a professional hat. But because many of us are actually EV owner-drivers, as I am myself, I thought I'd start with a little personal touch, and then we can get back to the business later on. I'm going to talk about fast charging. I'm going to talk about why we need it, why it's such a good idea, and why it's going to create a transformative user experience for drivers of electric cars. And I imagine most of us probably haven't experienced this yet because there's not a lot of infrastructure in the ground today, but Fast Cities is certainly one of the companies that's going to change that very soon. So rather than introducing myself, let me tell you about the last 20 years. 1998, I was a university student at UQ, and that was the year that we ordered our very first lithium-ion battery pack for the Sunshark solar car. So 20 years ago today. And that was, to my knowledge, one of the very first applications of lithium-ion batteries in an electric vehicle anywhere in the world. We weren't one of the first, but there was not many around then. And obviously Tritium, which many of you would have heard of, the fast charging company, also emerged from this project. So, it goes back a long way, but pretty significant start there. 5 years later, so fast forward 5 years, it's now 2003, and I'm doing a PhD along with a bunch of other people at the University of Queensland. And this car, the Ultra Commuter, was the first design study that we know of in Australia to try and make a practical electric car using the latest technologies, including lithium-ion batteries. The charging of this car, of course, was very prototypical, I think, carefully controlled, certainly not fast, not even slow. Terrifying would be the best word for it. But, there's a little bit of progress here. So that was 5 years later. Fast forward another 5 years. It's 2008. And there's a young Australian engineer driving that Tesla Roadster across the Bay Bridge in California, and that car had just entered production. So the Roadster was the first car in the world that demonstrated the full potential of lithium-ion technology. This car had 400 kilometres of real-world range. I know it because I proved it. And didn't have fast charging though. It had AC charging at up to about 20 kilowatts. But was certainly a sign of things to come, and we know what happened with Tesla after that. Fast forward another 5 years. So now it's 2013. I'm back in Australia now. Tesla has just entered production of the Model S the year before, and it's a really nice car, I've got to say, probably arguably their best product. But very expensive car, especially in Australia. And I would have loved to buy one, but I couldn't afford it. So I bought an iMove instead. Also a lithium-ion battery vehicle, not the same range as the Model S, but it did have fast charging, 50 kilowatts DC fast charging. So along with the Nissan Leaf and the Tesla Model S, some of the very first EV products in the world that had fast charging capability, although at a slowish rate relative to what we're looking at today. Fast forward 3 years now, so now it's 2016. And Tesla's making the Model X, which was the first electric SUV in the world. It was also all-wheel drive, it could also tow, and it of course had fast charging as well. And by this stage in Australia, we were starting to see a bit of a supercharger fast charging network being built out. But again, very, very expensive car, even more expensive than the Model S. So we bought an Outlander. Could do everything that a Model X could do, and actually arguably do it better, except that it did burn a bit of fuel. So unfortunately there wasn't a fast charge option available to us at that time, but that basically brings me on my personal journey to where I am today. So that's 20 years of EV experience that I've had so far, And as you can see, fast charging come into the mix, but you know, some products have it, some products don't. We're not quite there yet. Let's look forward, beyond 20 years. So our IMEV is 5 years old now. The range is starting to degrade a bit. It is a bit of a slow car when it comes to the fast charging connection. So my wife and I are in the market, and here's 4 cars that we are actively looking at today, and I'm sure you will recognise them all. So we've got the Hyundai Ioniq, the new Nissan Leaf, which is just parked outside, the Hyundai Kona EV, and of course the Tesla Model 3. Now, these 4 cars all have 3 key things in common. The first is their drive-away price will be under $60,000. Some of them will be under $50,000, which is starting to get into the realms of affordability for people like myself. Secondly, they all have lithium-ion batteries, and they all have a real-world range well in excess of 200 kilometres on a charge. Real-world range. So, you know, the idea that you drive from Brisbane to Noosa or Brisbane to Byron Bay, no problem. You might have to charge to come back, but at least you can get there, which is something that previous products, apart from the really expensive ones, couldn't do quite easily. And last but not least, they are all enabled for DC fast charging. And apart from the Nissan Leaf, which has still only got a 50 kilowatt connector, all the others have a connector of 100 kilowatts for their DC fast charging. So electric cars have certainly come of age, and I'm serious, we will be buying one of these as soon as we can get our hands on one. We haven't decided which one yet, but very, very soon we'll be buying one. So the question now becomes, the cars are ready, how are we going to charge them? When I drive to Noosa, or Byron, or Sydney, dare I say, how am I going to charge it? There is no infrastructure commensurate with the quality of these cars. Not yet, not in this country. There's a few fledgling networks. We've got the Queensland Super Highway, and we've got the Western Australian network, and we've got NRMA building a 50 kilowatt network, but they're just getting started, right? We haven't got national coverage. And furthermore, the nature of those charges is limited. They're 50 kilowatt charges, right? My IME 5 years ago could handle that. The latest cars can go much faster, and we need to keep pace with the infrastructure, because the cars are just going to keep getting better. We know this is going to be happening. And so we're now looking at what we call ultra-fast charging, which to me means anything above 100 kilowatts. This photo is a photo from Germany. It's the very first ultra-fast charging site built in the world. It was commissioned in March this year, and the network there is Ionity, actually founded by the 3 big German car companies, and with the charger supplied by Tritium. So what a coup for them. And so this opportunity, if you like, was what catalysed the formation of Fast Cities here in Australia, to think about how can we provide this level of infrastructure, you know, the very top end, top quality infrastructure, so there's no limits to EV uptake going forward. So what I'm going to do now is talk a little bit about what this future looks like. Not in terms of business plans, but just in terms of the user experience, the technology, sort of the shape and feel of it from an engineer's perspective. I'll quickly put up this picture just to show you that we're not kidding when we say we're building a national network. This is our current version of the rollout plan. I'm not going to give you too many details on site locations because they're confidential until we launch, but we will be launching a site very soon, and it will probably be pretty close to Brisbane, so you can all watch and wait and see. We're not the only operators doing this, of course. There are other networks starting up too, so we're pleased to see that, because it really means we're not the only ones who think this way. But that's the scale of the network we're going to build. Now that shows you the geographic coverage. What I want to talk about is why we are going for the very top of the line ultra-fast chargers. There's a good reason for this. If you're driving a top of the line electric car, and for this example, I've assumed it's got a 100 kilowatt hour battery, just so you know the assumption behind it. If you're driving your top of the line electric car and you want to do a long trip using ultra fast charging, this is what it's going to look like. So this diagram shows on the vertical axis battery state of charge, on the horizontal axis travel time in hours, including driving and charging, and you can see the vehicle starts from home at 100%, drives for 4 hours or about 400 kilometres, and then it has to recharge. And since we're using fast charging, we need to be mindful of how we're cycling the battery. So there's a little buffer at the top that I've called the slow charge zone, that you can only really recharge into that with a slow charger, otherwise you might endanger the health of the battery, as Chris just spoke about. So typically your fast charging will stop at about 80% full. And then in the other direction, once you get below about 30% full, you might start to wonder, where am I going to charge next? So I'm calling that the pit stop zone. So that's the region where maybe the first hints of range anxiety enter your mind and you're like, okay, I need to fill up. Once you get down to 10%, of course, you're in the danger zone. You may run out if you can't find a charger soon. So in my experience, and I've got quite a bit of it now, driving on the road in the real world, that's kind of like what the use case looks like. And so you can see, to drive the 1,000 kilometres in this vehicle, we need to recharge twice. But because I've assumed they're top-of-the-line ultra-fast chargers, those recharge cycles only take about 10 minutes each, and we're completing the 1,000 kilometres of driving in just over 10 hours. Now, I haven't added all of the practical toilet breaks and time to plug in and plug out of just a simple example. So that's what you get from a top-of-the-line ultra-fast charger. What happens if you don't build a top-of-the-line ultra-fast charger network? Then you get these other options. The red one is basically equivalent to the Queensland Super Highway or the network in Western Australia with 50 kilowatt chargers. So it's still pretty good. I mean, let's not knock it. It's a great starting point. But if you look into the details there, you'll see after the first charge, you've lost an hour. And by the end of the trip, you've actually lost 2 extra hours because your infrastructure isn't fast enough. And dare I suggest you try to drive from Brisbane to Sydney, say, with AC charging only. The green line is what that would look like. So, come back tomorrow if you want to keep going. So when we talk about ultra-fast charging, we know it's, top-of-the-line equipment. But the whole point is we want to provide users the best possible experience. They don't have to do it if they don't want to, but we need to provision for it because the vehicles are getting better so quickly. We need to keep pace with this infrastructure. So what I'm going to show you now is what 350 versus 50 kilowatts looks like on an engineering level. So you can really understand why it's such a big difference. So on the left there is the operating envelope for a 50 kilowatt DC charger. The axis at the bottom is DC current in amps, and the vertical axis is the DC voltage. And charter mode, which we all know very well, was limited to 50 kilowatts, and that constitutes a 125 amp current limit, a 500 volt voltage limit, and then a 50 kilowatt power limit. So anytime I charge my iMe from a fast charger, I'm stuck somewhere in that envelope. I can't go outside that envelope. It'll maybe consume 125 amps and it may rise up to 500, but it'll never go above 50 kilowatts. On the right, the blue, is the ultra-fast charger. And this is indicative of the Tritium product, which I showed you installed in Germany. Now the current limit is 500 amps, and that's because the cable and the plug are liquid cooled. And the voltage limit is up now above 900 volts, and that's because automakers are starting to make vehicles that have battery voltages that high, and the power limit is 350 kilowatts. And you can see it's a massive envelope compared to what we had before. That's a world of opportunity right there. Basically, any production car that's coming to market for the foreseeable future will be able to operate somewhere in that space. And if your car isn't capable of taking the full 350 kilowatts, well, that's fine. You can still find, your natural operating point in that envelope. The key point is, by building the full envelope, we enable the full possibilities for all cars, all customers, and every possible type of trip they might want to do. So here's what the market looks like today in terms of products, our customers. On the bottom axis, we've got battery energy in kilowatt hours. On the vertical axis, we've got the time to do a recharge of 60% of the battery's capacity, as I showed you in that real world charging scenario there. We're actually cycling the battery about 60% in practice. And so that's what the recharge times look like. And then just to make this diagram really complicated, we've also got the power levels, those diagonal lines. So if I just start down the bottom here, there's my iMe down the bottom. Now for a car that's 6 years old, we'll forgive it, all right? It's the underdog here, but it was a long time ago now. As we move up this line, the 50 kilowatt line, we start picking up other products like the Nissan Leaf and or the old Nissan Leaf and now the new Nissan Leaf, and I forget what the others are, but there's still a couple of 50 kilowatt cars in the market today. Then we've got a couple here that are on the 70 kilowatt line. I think they're the Hyundai products. And then over here we've got a couple that are around the 100 mark. So that includes the Teslas and the Jaguar and the Audi and the Mercedes and the new ones that are coming to market in the next few months. That one there I think is the Mercedes with 150 kilowatts DC charging. This one down here is the really exciting one. It's the exception to the rule today, but it's the exciting one. It's the sign of things to come. That is the Porsche Taycan Mission E, however you may know it. A car with almost 100 kilowatt hours of battery and 350 kilowatts of charging capacity. So you can fill that car up in 10 minutes. It's astonishing, and that is the first production car coming to market that has validated that. Obviously most of these other cars can't take full advantage of 350 kilowatts today, but we've got to build for the future and also cater for all of those other products too. So that's what the marketplace looks like today, and that's why we are building a 350 kilowatt network, because we know these customers are going to be available today, but we also know what the future holds. And just to expand on the future, these are the trends. So we started down the bottom at low energy capacity and small a low charging power. And then over time we've moved up to bigger batteries, but because of the bigger batteries we've had to use faster charging to keep the recharge time in reasonable limits. As we keep going forward though into the future, we're starting to find ways to bring that charging time down to the point where we can potentially charge a car in 10 minutes flat. And so what happens next? Well, over time, the passenger cars will just keep getting better. They'll retain that battery capacity and the charging time will keep coming down. And as an example of that, here's the Tesla Model 3, right on the edge of what I would consider to be the sweet spot for passenger car fleets. So think Ubers, taxis, people who are driving all the time and they don't want to stop. Or if they do have to stop, they want to stop for the bare minimum amount of time. And then similarly, commercial fleets, so logistics operators like Australia Post, Toll, Woolies, anybody who's delivering you boxes and parcels, again, they want to keep driving, they never want to stop. And if they do have to stop, they want to stop for the bare minimum time. This is what we know the future holds for this technology. And so, Fast Cities is going to be spending a lot of money to build this network because it's going to be fairly expensive to do, but we are very confident that we are building for the future of electric vehicles that we know is coming soon. So that's all I had to say. Thank you very much.